Okay, that was the one where you're looking at it's cut at sort of an angle. Okay. So first, there's the first quiz is on Monday. And then exam 1 is on a week from today, next Friday. I think that's the 2nd. Is it? You're my go-to date confirmation guy. 2-2. Okay. And topics, did I say? I think we're going to call this up through strain and constitutive relationship. By the way, I never said, I don't think, what constitutive means, but the constitutive relationship is the relationship between stress and strain. So in our case, the constitutive relationship is this. You can imagine there are other relationships, but this is the one that assumes a linear relationship between stress strain, that we're in the elastic range of the material, so when you unload it, it'll spring back to its original shape and size, and small deformations. Oh, and also isotropic. Okay, so the homework question is the one where you have a circular cylinder and there's a load on the face that's the load's just horizontal like this. Okay, and it's distributed over the whole face, but the total is 12,000 newtons. And what's the diameter of this tube? Or it's not a tube, is it? Okay, so 0.04 for the diameter. And there's an angle. The angle between this and the face is 70. And what we need to do is figure out how to express that total force as a traction. We need that in force per area. So we just have to figure out what the area of that shape is. And if you think about what happens when you cut it at an angle, you're going to get an ellipse. And here's the relationship between the cross-sectional area if you slice it like this, and the cross-sectional area if you slice it like this. Let me try that again. Okay, well, so this distance is 0.04 meters. Just like this distance is 0.04 meters. Okay. And so everywhere that you can measure the distance across on the circle, you can measure that same distance across on the ellipse. It's just stretched out a little bit. So the way I thought, hey, that looks like a Teenage Mutant Ninja Turtle. So the way I thought about it is, say, divide this up into 10 strips, okay? Like strips, you know. You could also divide this one up into 10 strips, and the average thickness of each one of these 10 strips would be the same, you know, the width would be the same as the width across over here, right? You buy that? So like if so this strip over here corresponds to a strip here. It has the same thickness, just this one is a little bit stretched out vertically. Okay? And so to get the area, you're just going to add up the areas of these strips. Okay? So if we can just figure out how much thicker vertically each one of these strips is, then the total area is just going to be multiplied by that amount. You can see it for one strip, and if it's true for each one of those strips, it's true for the whole thing. Who here thinks this is an important, like a crucial topic in mechanics of materials? You're all correct. This is the least important thing in the world. Yes, I think it might be. Okay, so let's keep going. So now we just have to figure out how much it's stretched. And how much it's stretched is just determined by so here's a side view. We know this angle is 70. Make this a right triangle. This distance is 0.04. We just have to figure out what this distance is, and it just comes from, whoops, that's. Okay, so the hypotenuse is, well, hypotenuse over, no, 0.04 over the hypotenuse is equal to sine of 70. And so h is equal to 0.04 divided by the sine of 70. And that's the, whatever that number was, 1.06 or something. 1.064? Is that right, Scott? Times, well, what? So it's 0.04 times 1.064 is the hypotenuse. You can think of, so anyways, the area is pi times 0.02 squared times 1.064. That's just how much, And so now that you have the area, you can calculate the traction vector as 1 over the area times a vector in the negative x direction of negative 12,000. That gives you the traction vector. Yep. Yeah, so 1 over sine of 70, I think, is 1.064. So that's just like a scaling factor at 1.064. That's how much thicker each one of those strips is on the ellipse than the corresponding strip on the circle. Yes, because all you're doing is increasing the height of each strip. So this is how this problem came about. I made up that problem. I assigned it before I'd done it. Then when I did it, I realized you had to do all this stuff. Damn it, I already assigned that problem. And so then I had to do it, but it's not it's much more time consuming than its worthiness. Mm-hmm. Oh yeah, you knew the, yeah. Okay, yeah. Okay, right. That's a good way too. I just thought of it in terms of these strips. Yeah, all you're doing is thickening these strips. Yeah, right. That's right. Yep. Yeah. Yes, that's right. Okay, let's never talk about that one again. Yeah. Anybody have any homework questions? That's a homework question. Any other homework questions? So we're not doing 13? That's 13? Yeah. Well, now I've already done it, so you might as well write it in there. Oh, yeah, right. I probably just added, right. It's referring to the wrong. So I think it says something about calculating stresses and strains. Yeah, that you got from the tensile test. And you're supposed to use the last problem where there was a tensile test, I think. Does that make sense? Right? Oh, okay. Okay. Yeah, so the idea is just that I gave you the results of a tensile test. You use that to calculate E and Poisson's ratio. And then you use that E and that Poisson's ratio to do stress and strain calculations. Yeah. Yes. Do you have it here? Or
So 6, 8, and 13 refer to question 4.
yeah, so it refers, I don't have that with me, but it refers back to the last tensile test number. So this is like how you would do this. I mean, this is a pretty pretty practical way that this would all go. So you want to know what's happening in some loading using a certain material. So you take some amount of that material, form it into a sample, put it in the MTS machine, do the tensile test, use that to measure Young's modulus and the strain, and then put those values into your calculations. That's the idea. It would have made more sense if I would have referred to the correct numbers. But that's a good idea. It's called what? The stress strain tensile testing thing? I did not know that. Huh. Load frame. Uh-huh. Right. But I mean, you can imagine how like precise everything has to be because we're talking about such tiny changes in length, you know. You have to, yeah, yeah. Well, with rubber bands, it would not be hard, you know, because you apply 10 newtons of force to a rubber band and you get 0.27 centimeter, 0.27 meters of, you know, it deforms all. So yeah, you could do that with a ruler, no problem. But it's pretty different when you're talking about microns of deformation, you know. Okay, so 11, right? 11? Um, so the material from number 10, do you happen to have the Young's modulus and Poisson's ratio for that you got from number 10? On strain and constitutive relationship? Okay, from number 10, E is, okay, 1.05 times, oh, okay, so 1.0 times 10 to the 11th pascals. Okay, and then or 100 gigapascals. And then Poisson's ratio? 0.12. Okay, so that's the Young's modulus is right in the ballpark of like copper, I think. The Poisson's ratio is very low compared to any metal value that I've seen, but so that's our material. And then number 11 asks, well, it says that the Voigt strain is 0, 0, negative 5 times 10 to the minus 5, 0, positive 2.5 times 10 to the minus 5, 0. And what are the units on that? On the strain? No units. Pure number. What's the stress tensor? So first, to get the stress tensor, we know that the Voigt stress is equal to the stiffness matrix times the Voigt strain. How do you remember that this is the stiffness matrix and not the compliance matrix? No, how do you remember to write the S? I mean, that's makes sense. That changes the whole question. Yes. Yes. So this is going to be big. This is going to be little. So this has to be big. And would you consider steel more stiff or compliant? You know, like all the metals, all the materials we deal with are stiff. So now how do we get that stiffness? Well, we know the compliance matrix is 1 over E. You know, hopefully at some point you'll have this programmed into your calculator, but it's this thing. Sure. And so then to get the stiffness matrix, you just invert that. Okay, so any questions about that? Yeah, so first I ran that compliance program to get the compliance matrix, and then this calculator, at least, you can just use the power thing to the -1, and it interprets that as an inverse matrix if you do it with a matrix. And so then for part B, it asks you to express this in a rotated coordinate system. So first, right now we have the Voigt stress. To do any kind of coordinate system transformation, you have to represent that as a tensor. So just reformat this. So that's -7.05 times 10 to the 5, -7.05 times 10 to the 5, -5.17 times 10 to the 6, and then 0 there and there. XZ 1.11 times 10 to the 6. And down here, and then zeros here. I did, well, so you could just plug it into, there's a program called like Voigt to matrix, I think, V2M, I think. But you just have to remember what the elements are in the order of the Voigt notation. This is the XX, YY, ZZ, and YZ, XZ, XY. And so now I just put those in here and took advantage of the symmetry to get the other three that aren't given. This is Pascal's. And now that we have that, to do a rotation, so the rotation matrix for -45 degrees about the y-axis is cosine of -45, 0, negative sine of -45, 0, 1, 0, sine of -45, 0, cosine of -45. And then the stress tensor in the new transformed coordinate system is just Q times the stress tensor in the old coordinate system times Q transpose. And you might have the program in there that does tensor rotation, and you can skip all this and it just asks you to input the old stress tensor and the angle, which would be -45, and the axis, which would be 2. And it does all that for you. You get out that in the new coordinate system, the stress tensor is -1.83 times 10 to the 6, 0, -2.23 times 10 to the 6, -7.05 times 10 to the 5, 0, 0 there. This is -2.23 times 10 to the 6 because of symmetry, and then -4.05 times 10 to the 6. megapascals. And the syntax that I used there is I took this stress tensor and put it in the matrix S, and then for this I went tensor rotation S -45 2, and it gave me that. And then what's the Voigt strain in this coordinate system? Well, the Voigt stress in this coordinate system is -1.83 times 10 to the 6, -7.05 times 10 to the 5, -4.05 times 10 to the 6, and then YY, XZ, XY, and then the Voigt strain is just the compliance matrix times that Voigt stress. That's the strain in the new rotated coordinate system. So anytime you want to transform the coordinate system, you need to do it through stress and then recalculate the strain once you're in that new coordinate system. Oh, and it asks something about the stress cube. So we have a compressive stress along the x-axis of 1.83. I'm going to do these all in megapascals because I'm out of room. The y direction, that's compressive because it's negative. So 7 point, nope, that's times 10 to the 5. So this would be 0.705. And then z, we have a compressive stress of 4.05. And then the only shear stress is xz. So that's negative. So this way and this way. And those would be 2.23. Any other questions about that one? Yeah.
So on an exam, do you want us to write out all those steps? You just say Wolfram alpha after we set it up, and then say Wolfram alpha. Do you want?
So which steps are you curious about?
Do we write down every single transition?
I would recommend writing down. I would recommend sort of covering your tracks. Like if you just write down numbers here and they happen to be wrong because you punched something in wrong, I have no way of knowing that if you haven't said what you're doing, you know. So if you write this down, you get full credit if you screwed something up here. If you just go to here, you lose almost everything because I just don't have any idea what you did, you know. So I would recommend writing mainly all this stuff. You don't have to tell me how you did the calculation. I mean, I'll just assume that any calculations you're doing in some kind of calculator, you know. But yeah, I would recommend writing the equations that you're using to get that stuff. But if you just went through, if everything was right, if everything worked perfectly, and you just gave me this and this and that, I'd give you full credit for that. But it's just sort of, yeah, it's just insurance in case something goes wrong to let me know what your overall plan is. Because you have to, especially like in this class, you have to type a million numbers in. You know, it's pretty easy to something off by a factor of 10, and then everything's haywire. Oh, yeah, right. Yeah. And that's something interesting about doing this kind of stuff. I think actually is in a class it doesn't matter. Like I just look at it and I'm like, yeah, you had the right idea. Blah blah blah. Get it all right. But if you're sending this to somebody in a company you're working for, like that's
not gonna read it.
I mean, that's bad news, and so so a lot of this stuff is about coming up with like independent ways to check your answers, multiple ways to do this stuff and make sure that it's all basically telling the same story. I mentioned that sort of when I was talking about finite elements, like you go and you do your finite element thing, you get numbers, but no one would ever just assume that those numbers are right and move on from there. You need to do simplifications and make sure that that's telling a similar story and see what happens if you change this, and does that make a small difference, and like little by little you do all these calculations and you finally convince yourself like I really know what's going on, I understand why the results are this, so
Do you ever get like a professional engineer and they're just like, yeah, that's right. I just know it's right. And they don't do anything.
I'm happy to say that I've never really had to work with other people. It's one of the great joys of my life that that's the case. But I mean, I used to, my one job outside of teaching, I was the one engineer in this biomechanics lab, and these people would come in for a surgical plan or whatever, and I wrote all the software for our lab, and I did the tests, and and there was no one else, the people I would give my results to were like surgeons. They were like, I'm like, cut here, and I'd be like, yep, I'm confident, and so like everything that I did was like the calculations were part of it, but then most of what I spent my time on was like, how can I do these calculations multiple ways? How can I approximate them? How can I, look at it in all these different ways that all tell me the same story, so that, somebody in 5 years doesn't limp in and kill me, like, you attached my leg to my head.
Is that how you got the job? Somebody did make a mistake?
Yeah. Exactly.
I swear it goes there.
Yeah. Yeah. Can you go back and check that equation real quick? Like in their surgical stuff. Hey, can you recheck your calculation? Any other homework questions? Okay. It's a weekend. So what did I say? Quiz on Monday.
Wednesday.
No. Quiz on Monday, test on Friday. Yes, thank you.